Okay. So, I don't know if you noticed, but there's actually an obvious flaw. Well, I don't know if it's obvious of this argument above. Well, we'll start. What's the problem? Well, in order for this argument to work, remember we're trying to show that two paths are homotopic, then they integrate the same thing if f is holomorphic on this region that allows this homotopy to occur. Well, it involves showing that in nearby curves, throughout this homotopy, um, the integral is all the same, and therefore the initial curve and the final value, right? But here, that's the problem when you say it like that. It's establishing the fact that the integral is the same between gamma 0, this curve, and the next curve. But how do we even know the second curve, quote unquote, is actually a curve? That is to say, how do we know that this is piecewise smooth, right? Like per our definition of how we can define these integration. That is to say, are these integral even defined, right? Because to do this, we use FTC, and that kind of required our function to be, at least the curve to be differentiable, right? So we can actually perform this calculation. So that's a problem. So maybe I'll write this in red, but here's a problem. The problem with this argument, not really slight, but I'll put slight in quotes, problem in this argument. Okay, how do we know this gamma SI are also curves, right? I.e., given the homotopy, F, how to write it, FTS maybe? Doesn't matter. How do we know for each S, this F dot S is a curve for our integration? So that's a problem. Because all we know is that FTS is continuous. So we know that this fixing the S, what we will get is continuous. So we know this is continuous. Let's just put in T. Curve in T. We know this is continuous in T. But for our integration, we demand the curve to be piecewise smooth. And our definition for smooth is even very restrictive, right? We need to have z prime of t to be continuous, and z prime of t is not equal to 0. So we need these two conditions. That is continuously differentiable and non-vanishing. Well, turns out I don't really think we need this ever. So I'm gonna cross this out because this one is gonna will give us some trouble later, and you'll see. But at the very least, we still need z prime of t to be continuous because, well, at least we want to guarantee that when we integrate something like this, gamma f of z dz, we can write this as, from a to b of f of z of t z prime of t dt, and then if this is all continuous, then this exists, right? So this is the only reason why we demand z prime to be continuous, so that in this definition, this integrand is continuous, and then we integrate a continuous function, this will always be okay. So that's the problem, because for each slice, for each s, this FTS is just continuous in t. We know that if the derivative with respect to t even exists, so basically the partial derivative with respect to t exists, and we don't even know if it's continuous, right? Let alone if it's non-vanishing. But we're gonna scrap this. This is I don't know, at least so far I'm seeing it, kind of useless. Okay. So what's an idea? So the idea is what I'm gonna do is we're gonna estimate. Given that you're homotopic, okay, there's a continuous homotopy, we can estimate this to a smooth homotopy. In fact, we're going to estimate it so that each slice is a polynomial. Yeah, do it in a polynomial way. So, right, so how am I going to do this? So the idea is this. I'm going to redefine our curves to be just continuously differentiable, piecewise continuously differentiable, okay? So before the idea, we're going to redefine, we'll be defining curves like, continuous differentiable and not vanishing, basically regular, but I'm going to redefine our curve to mean piecewise continuously differentiable. That is to say, its derivative is continuous. Okay. All right. So now, given two curves, here's the idea to make this work. Given two curves, gamma 0 and gamma 1, okay. First, let's say there are homotopic, say, and I'm going to use big H this time for homotopy, just because. Say H of TS is a homotopy from gamma 0 to gamma 1. Again, the endpoints are all fixed and all that stuff. Ooh. How do I make sure the endpoints are fixed? Well, we'll cross that bridge. Okay. So we know that this is continuous. On 0, 1 cross 0, 1. And what I'm going to try is to estimate this with polynomials. So by Weierstrass theorem, we can use Bernstein polynomials to estimate that. So can estimate, can approximate HTS by polynomials. BXY, I guess BTS, uniformly. Okay. So that's the idea. So this is Weierstrass theorem. Okay. And the reason why we'll use B, because we can do this with Bernstein polynomials. Okay. And let's see. So how are we going to define this? So we're going to define Bernstein polynomials to be, we're going to call this of, okay, so given this F, given our homotopy HTS, define, which is continuous, right? Um, define Bn1 and 2 OTS to be the summation of K1 from 1 to N1, K2 from N to N2 of H. So the idea is we're going to sample this thing in a uniform grid. So what does that mean? K1. Should I start from 0 then? Yeah, we should start from 0 because we're sampling the points on a grid. And then putting some polynomials. Okay, so N1, K1, T to the K1, 1 minus T, to the N1 minus K1, S to the K2, 1 minus S, N2 minus K2. So we're going to leave that to the end, but I claim that this approximates H uniformly. So we claim that BNN converges to H uniformly on 0, 1 cross 0, 1. Okay, so that's the idea. And so what's nice is that this is a polynomial. In ST. Okay, these are called the Bernstein polynomials. And as you can see, what we're doing is we're just chopping up, the domain of H equally, and we sample the values of H, and then we just multiply by the appropriate parts. Okay. So what does that do for us? Let's actually look at what happens at the boundary points, because we know the homotopy has the following property, that at one endpoint it is always equal to A, right? So basically it's a constant. And at the other endpoints it's also constant. right, for all s. This is saying that our homotopy, fix the points right, for each s. When t0 is always at a, they all start from a and go to b, like that. Okay, so does our polynomial follow the same thing? Let's see. What is b n n 0s? Well, 0s because we're plugging in 0 in, anytime there is a t to the 0, t to the k1 power, where k1 is not 0, that's just gonna give us 0, right? So the only term that will left is if k1 is 0. So we get sum k2 equal to 0 and 2h k1 and 0, so we have 0 k2 over n2 and 1 n, so I guess this is k2 to n choose 0, which is 1. 0 to 0, we're going to that is defined to be 1 times 1 minus 0, that's 1 power, s to the k2, 1 minus s, n minus k2. So we get this thing. But because this is always a, so we get a factor of a out times the sum of k2, 0 to n, sk2, 1 minus s, n minus k2. Oh, I guess I forgot another factor of binomial coefficients. Okay. So looking at this, well, we recognize what this is, right? This is just the binomial expansion. This is just the binomial expansion of s plus 1 minus s to the nth power, which, lo and behold, is a. So that's reassuring that the Bernstein polynomial fixed the endpoints. This is reassuring. Okay. What about b n n 1s? This is the same story, right? It's gonna be the same story. When it's 1, if n1 minus k1 is not 0, they're all gonna be 0. So the only term left is if this is n1 is equal to k1 is equal to n1. So if k1 is equal to, then we get k2 go from 0 to n, h1 comma k2 over n, n choose n, this is going to be 1 times 1, right? N choose k2, same story, 1 minus s, and 2 minus k2. So we can, these are, people don't talk about the Bernstein, but these are very nice constructions to solve the problem. Wow, this is just amazing. I think. Didn't even expect this. Now this is a constant, so this is b because h fixes the other endpoint at b. And of course, the rest, this is just unchoose k2 of sk2, 1 minus s n minus k2. Again, we recognize that as 1 plus 1 minus s, the binomial expansion of this, like that, which is 1 to the n, so that is equal to b. Okay, so not just that this converges uniformly, if H is the homotopy, which fixes these endpoints, the B's will also fix the endpoints. Conclusion: if H is a homotopy, fixing endpoints AB, so will the polynomials B and NXY also fixes AB. Very, very neat. And they are polynomials. Now, would it matter that H takes value in complex? Well, not really, I don't think. Right? Don't think so. I don't think so. But we're gonna have to come back and check that. But anyways, so this works. So what I'm saying is now instead having a homotopy, draw like that. This is the image of some f. We now have some other version. Now that all the curves are just polynomials, which obviously are continuously differentiable. Now, the first curve, of course, don't match, and the last curve don't match. So what we need to do is then linear homotope it to this. So for the first curve, so let's call this first curve beta. So this is our gamma 0, gamma 1, this curve. Now this is some B and N that does this job. Let's call this B epsilon because this is just saying that we can make this image within epsilon of each other. Let's call this first curve beta 0 and beta 1 here. Then this is saying that the soup difference between beta 0 and gamma 0 is also between epsilon away from each other. And right. So what we'll do is we'll define homotopy, an additional homotopy from gamma 0 to beta 0 linearly. So linear homotope. The n curves. So that is to say we have a initial homotopy. Let's call this H0 TS. And simply take 1 minus s gamma 0 t plus s beta 0 of t. So this is piecewise continuous, piecewise differentiable, piecewise continuously differentiable, right? Because gamma of 0 is piecewise continuously differentiable all the way to beta 0, which is going to be, in fact, smooth. It's a polynomial. Hit beta. And similarly, for the other curve, you also do the same. So I think this then fixes everything. Piecewise C1. Right. And we also do the same for the other, so the gamma 1 curve to the n curve of the Bernstein polynomials. Same deal. Also piecewise C1. And the only thing that we need to make sure is that they all fit inside U, right? And yeah, so we can calculate this distance to F. That should all be less than epsilon away. So the final thing that we need to set final detail make sure you know, the image of B is in U. And so is there another detail that I said I need to watch out for? Yeah, so there's no hope in, oh yeah, the complex. So does it matter? This complex. Well, I had to work through the proof of this again, right? This claim. Okay. So this, of course, deserves some work, some looking into, which is basically proving that this actually works. And it should. And we should also make sure that the image is in U. Now this is okay because the F is, F is compact. The image of F is compact. So when we approximate this, this is the image of F, because it's compact inside some opposite U, there is some open protected ball of some radius, right, around it. We say this radius is 3 epsilon. Then our ball, because it's epsilon away, so this should be roughly within it. And then we also need to make sure that these two n curve homotopies are also in U. But this is linear interpolation, so this should be all nearby. So that should be the idea. So this just needs to be a fix. So the idea is then, sure, if two curves, again, redefining curve to not have to have derivative equal to 0, because I cannot promise that the derivative of these polynomials are not 0, but if you have two curves are homotopic, then there exists another homotopy that is a smooth homotopy. In fact, that is a piecewise C1 homotopy. Okay, so the idea is if it's continuous, then there exists some homotopy that is piecewise C1. And also hopefully lands in U. And that will allow us our argument to work, because then we just work through that using that piecewise C1 homotopy in order to be able to calculate these integrations. So that's a tiny detail. Okay.